Previously in data structure class of video lectures, so we talked about a few applications of a stack. First one is a maze problem. Okay, so we use the stack to hold all the alternative options, right? So when we take an options, when we have a couple of different options for the direction, then we select one option, and at the same time we save all the other options, right? So that's how we use the stack in the maze problem. And in the second applications, we use the stack to evaluate postfix expressions. Right, so I got this figure from the previous lecture. So given an infix expressions, we didn't talk about converting yet, but let's assume that we have a converting algorithm so that we get the postfix expressions. Okay, and once we have a postfix expression, then we know how to evaluate these postfix expressions. So we talked about the algorithms about this evaluation using a stack. Okay, so today we will talk about an algorithm to evaluate the postfix expressions. Okay, specifically, and then next we will talk about how to convert an infix expression to a postfix expression. Okay, so given this infix expression, the first step is to convert the infix expression to a postfix expression. Okay, that's the first step, and then second step is actually evaluation of a postfix expression. So to evaluate a postfix expressions, we need a tokenizer. The postfix expression is actually a string or character array. Then we have to get the parameters. We have to get the operator, then operands. Then we know what to do, right? So the input is just a string. So we need a tokenizer. So what is a token first? So token is usually a word or an atomic element within a string. So in these infix notations, 15 is one token and plus is another token. A is /2. They are tokens. And in the postfix notation, the same thing. Okay, so 15, A and 2. These operands and operators are tokens. Okay, so usually in a string, we can define what is a token. And in an expressions, operators and operands, these are the tokens. And these tokens can be obtained by a process called tokenizing. And the tokenizing is to split up a string of characters into a set of tokens. So again, given this 15 plus a divided by 2, then we will get the 5 tokens. Okay, so basically tokenizing is not a simple function, not a simple process, because sometimes, as you can see here, one token can be just one character, but sometimes it can be 2 characters, 3 characters. Okay, and sometimes the space, white space, is a good delimiter, but sometimes we don't have white space between the operand and operator. Like in this example, a divided by 2. We don't have a space between a and slash, but still a is an operand and the slash is operator. So these are separate tokens, even though they don't have a space between them. Okay, so sometimes we have white space, sometimes we don't have white space. Sometimes tokens are long, sometimes tokens are short. So it's not a simple function. But in the next slide, we will see a simple tokenizer, get token. Okay, the input is a string and an index. Input is a string and an index. Okay, and then output is a token. Here is a simple tokenizer, get token. Okay, we can use this tokenizer for postfix expression, or we can use this one for an infix expression too. Okay, but in the next slide, in the functions, we will call these get token functions to evaluate a postfix expression. Okay, So that in that case, expr is a postfix expression as a global variable, but we can use this function to tokenize an infix expression like this example. Okay. So when we call these functions, we actually pass one character variable's address and integer variable's address. So in this function, we have character pointer variable and integer pointer variable. And n is actually pointing one integer variable from the caller functions, and from the caller function, that integer variable is actually indicating the location of the character in the expr variable. For example, if it starts from 0, okay, so if it is a 0, then expr star n plus plus will return 2 in this example. If the expr is 2 times left parenthesis 3 minus 1 right parenthesis, if the expr is like this, then it will return 2 for the first time. So the star symbol will be 2, okay? And then we have a switch statement. Depending on the value of a star symbol, then we return left parenthesis, L paren, R paren, and plus minus divide times mode, and end of string and operand. Okay, so let's see these cases first. So since we are talking about the postfix expressions, we don't have left parenthesis and right parenthesis, okay? And we can have a plus, minus, and slash, star, and modular. And whenever the character is one of these, then we will return plus, minus, divide, times mode, okay? Otherwise, if it is a null character, then we will return end of string. Otherwise we will return operand, okay? So if it is an operand, then we return operand. Otherwise, we return some information about the operator. Again, we assume that the operands are just one-digit numbers, okay? That's why this tokenizer is a simple tokenizer. Okay, here's an algorithm to evaluate the postfix expression. So in these functions, okay, this is an algorithm, okay, not an implementation of this algorithm. So we have a token and a symbol and two operands, and we have n. And n is the counter for the expression string. So it is indicating the location of the symbol, okay? And first we call get token. So we pass the address of this character variable symbol, and we pass the address of the integer variable n, okay? So after calling these functions, token will get some informations, okay? And then the symbol will get that character, okay? And then n will increase. Whenever we call these functions, n will increase by 1, okay? Okay, now we get one token, one just character or one digit, okay? Then if the token is not end of string, then we are in the middle of expressions, okay? Then we just check if token is an operand. If token is an operand, then we push that number, okay? So we can just push a symbol minus a character 0. You know, the symbol is just one character, so the symbol minus character 0 will be just integer, okay? You can just it's up to you. You can translate this character into the integer number, you know, in a different way as you want, okay? So anyway, as long as the token is operand, then we have to push. Else, it means it is an operator, okay? Then we have to pop two operands. So op2 will get the first one and op1 will get the second one. Don't get confused with this order, okay? The first one should be the second operand, and the second one should be the first operand, because we are using a stack, okay? So we should not change the order of these operands so that the first pop will return one operand to OP2, and the second pop will return a value to OP1. Okay, now we will check this token. Okay, so in the get token functions, the return value was about the operator. Okay, so we check this token, and if the token is plus, then we evaluate this OP1 plus OP2. Okay, and then the result will be pushed back to a stack, and then we break. If it is a minus, then we will evaluate OP1 minus OP2, and then we push the result back. Okay, so in this expression OP1 minus OP2, if we change the order of this OP1 and OP2, then result will be different. So don't change the order. Okay, and if it is times, then we multiply OP1 and OP2, and we will push. If it is divide, then we evaluate OP1 divided by OP2, then we push. And if it is modular, then we do that. We basically the same thing. Okay, then after this popping and pushings, and then we will get the next token. Okay, so we will call this get token one more time, and then we go back to this while statement. We check if the token is not null, and we check if the token is not the end of the string, and then we do the same thing. Okay, again and again. Okay, when the while loop is done, then where is the result? The result is actually in the stack. Okay, so we have only one value in the stack. That's the result of this evaluation. So we return the stack pop. It means we will pop, and then the value will be returned as a result of these functions. Okay. Now we know how to evaluate a postfix expression. Okay, so to implement a calculator, the missing part is to convert an infix expression to a postfix expression. So as long as we can convert, then now we can implement a calculator, right? Okay, so let's think about how we convert an infix to a postfix. So algorithm for human. First, to fully parenthesize the expression. Okay, so we just put lots of parentheses around the expressions, okay, depending on the order of these operators. Okay, and then move all binary operators so that they replace their corresponding right parentheses. Okay, so move all the binary operator so that they replace their corresponding right parentheses. So in this example, first we put all the parentheses depending on the order, and we move the binary operator right after the right parentheses. So in this example, the purple slash will go right after the right parentheses, right purple parentheses. Okay, and then the red minus will move right after this right red parentheses, and the blue plus will go right after blue right parentheses. Likewise, so all the binary operators will move right after the corresponding parentheses. Okay, and then delete all the parentheses, so that we can get this AB/C minus DE star plus AC star minus. Okay, that's how we get this postfix expression. Okay. Okay, here are two examples. Transfer the following infix notations into postfix notations. So we have A/B minus C plus D star E minus A star C with lots of parentheses already. So how can we translate? So try this one by yourself, okay? And the answer, what is the answer? The answer would be Basically, when we translate, we don't change the order of these operands. Okay, and then the order of these operators are the order of evaluation. Okay, so basically, A goes first, and the next one is B, and the next one is a C, and the next one is minus, and then D, and the plus, and slash, and E, A, minus, star, C, star. Are you following me? Okay, try this one by yourself. Okay, and next one, A slash B minus C plus etc. And in this case, again, we don't change the order of the operands. So A goes first, and then B follows, and then slash, because A slash B will be evaluated first time. So A, B slash, and C, and then minus, right? Because minus goes is before this plus operator. So A, B slash, C minus, okay, then D, and the E comes first, okay, D, E, and then star, and then plus, and A, C, star, minus. Are you following me? Okay, the rule is really simple. You don't have to put lots of parentheses and so on. You don't have to do that. Okay, just follow the order of operands, and then think about the order of evaluation. Okay, then you can just put the operators. Okay, let's think about evaluation of expressions. So in this case, expression is in the infix notations. Then the procedure is quite simple, as I said before. The first step is to transform in the infix expression to a postfix expression. Okay, and then the second step is to evaluate the postfix expression using a step. Okay, and the problem is about inefficiency. Actually, the evaluation of postfix notation is already simple. Okay, we already have seen that, and but the infix to postfix transformation requires at least two passes. So think about it. Actually, we put all the parentheses, okay, depending on the order, and then we actually move all the operators right after the corresponding the right parentheses. Okay, then we had to delete all the parentheses. So we had at least two passes. So we don't have to do that. No. So in the previous examples, how did you convert? How did you transform the infix examples into the postfix examples? Did you actually use a parenthesis? And then did you actually move the operator? And then did you actually delete all the parentheses? We don't have to do that. There is a much simpler way to do that. So let's design one pass algorithm to transform the infix to postfix. Okay, so given this input like A plus B times C, then we will actually go through these equations just one time using a stack. Then the output will be A, B, C, star, plus. Usually, sometimes when we think about one problem, and usually our brain humans are really smart, so we don't need a stack. We can just solve this problem so easily. But to computer, everything is something that is really simple to us might be really hard to a computer, and vice versa too. So in this case, the converting transformation is easy to us, but it's not that simple to a computer. So we actually give the exact directions to computer to solve the problem. So let's talk about the specific exact directions to computer for these transformations.